Hello there and welcome back to the Science Sleepy Minds. Outside your window the night is still and quiet, but inside your head something's stirring. A tickle of curiosity, a whisper of what-ifs. Imagine this. You walk into your room and something's different. The books are all facing the wrong way, your left sock is now your right, and your reflection in the mirror, it doesn't copy you, it stares back like it's thinking for itself. No, you didn't time travel and you're not dreaming. Well, maybe you are. But there's a deeper possibility crackling just beneath your pillow. What if the universe has a hidden twin? One made not of ghosts or fantasies, but of real stuff. Just invisible, untouchable, untamed. It's called mirror matter. And no, it's not science fiction. Though it sounds suspiciously like the plot of a late-night Twilight Zone rerun, it might be hiding in plain sight. It might even make up most of the universe. But here's the kicker. You probably won't survive this idea. Not because it's dangerous, because your brain might melt from the sheer weirdness of it all. So before you get comfortable, take a moment to like the video and subscribe, but only if you genuinely enjoy what I do here. And hey, let me know in the comments, what's your location and local time right now? Now dim the lights, maybe turn on a fan for that soft background hum, and let's ease into tonight's journey together. You trudge softly into the dark hallway of theoretical physics. It's creaky, full of cobwebbed equations, and each step seems to echo backward, like someone or something is following just 1 second behind, not in front of you. Not behind in space, but behind in symmetry. As if reality were being mirrored, not metaphorically, but physically. Welcome to the idea of mirror matter. Now don't panic, this isn't some evil twin plot, at least not yet. The concept of mirror matter suggests that, in addition to all the particles and forces you know and love, electrons, protons, photons, Monday mornings, there might exist a hidden counterpart to each, a duplicate. The kicker? This mirror version doesn't interact with our world the usual way. No light, no touch, no TikToks, just a ghostly gravitational handshake from across the veil. The idea comes from a simple, almost childlike assumption. Nature likes symmetry. If you've ever watched a snowflake fall, you've seen symmetry in action. Delicate, balanced, pleasing. In physics, we look for the same thing. The rules that apply here should apply there. The things that go up should come down, except sometimes they don't. This brings us to a delightful oddity. In the 1950s, physicists began to notice that nature plays favourites. Specifically, it has a thing for left-handedness. That's not a joke about your clumsy right-handed uncle. This is real subatomic particles. When they decay, sometimes do so in a way that seems biased. Like they're dancing only in one direction. No partner needed. This shattered a deep belief that the universe should treat left and right the same. Spoiler alert, it doesn't. So here's the big question. If the visible universe is left biased, could there be an invisible one that's right biased, balancing the cosmic equation? That's mirror matter in a nutshell. It doesn't just fix the asymmetry, it proposes a full-on secret universe. Not made of antimatter, which is its own thing entirely, but a true mirror copy, reflecting our own universe's structure, but flipping the chirality. You know, the handedness. Like looking at your reflection and realizing it's blinking first. And maybe, just maybe, that mirror realm is right next to ours, sharing the same space but hidden in another dimension of interaction. You could be swimming through it right now, and you'd never know. Of course, historians still argue whether the earliest notions of mirror matter were taken seriously at first, or quietly laughed out of lecture halls. Physics tends to be brutal that way. But slowly, over decades, the concept kept sneaking back into equations like a cat that refuses to be locked out of the room, too elegant to ignore, too mysterious to prove. One fringe tidbit that physicists like to toss around at conferences when things get sleepy. Some think mirror matter might be responsible for mysterious events like the Tunguska explosion of 1908, a cosmic blast over Siberia that flattened 80 million trees without leaving a crater. A mirror meteor, perhaps, slipped into our world just long enough to ruin someone's Tuesday. Now let's pull back and breathe for a second. If mirror matter is real, and it's a big if, it doesn't mean we'll suddenly see spooky mirror people walking through walls. In fact, they might never interact with us at all, except for one subtle, important force, gravity. That's the common language, and gravity, as always, refuses to keep secrets. So physicists started wondering, Could this hidden mirror matter be pulling on things, warping galaxies, acting like dark matter? Ah yes, dark matter, the ever-patient elephant in the cosmic room. It's invisible, it's heavy, it makes up most of the matter in the universe, and it doesn't play nicely with light or ordinary matter. You can't see it, but you feel its weight when galaxies spin faster than they should. Sound familiar? Mirror matter and dark matter might just be the same thing, or at least dancing in the same masquerade ball. So tonight, as you lie there listening, imagine the space around you, your room, your bed, the very air, as layered. In one layer, your world. Familiar, tangible, full of soft pillows and unpaid bills. In the other, a silent, untouchable twin, drifting just beyond your senses, watching, or maybe just reflecting. And you? You're not just a person anymore, you're a potential bridge, because particles might occasionally hop between these realms, but more on that later. For now, rest easy in the idea that reality might be a little more crowded than it looks, and somewhere, in the fold between shadows and light, your mirror self might be brushing its teeth, backward. You float now, weightless, back through time, into a world where scientists still smoked indoors, computers filled entire rooms, and every fundamental law of nature was up for grabs. It's the 1950s, baby. The atom had been split, the war had ended, and physics was having a bit of an existential crisis, because something very peculiar was starting to bother the minds that studied particles. Why didn't the universe behave quite as symmetrically as it should? You drift into one such mind now, that of a man named Tsung-Dao Lee, or maybe you're peeking over the shoulder of Chen-Ning Yang. The two are hunched over blackboards, running out of chalk and patience. In the world of theoretical physics, these guys are about to shake things up. At the time, there was a deeply held belief, almost sacred in fact, that the universe is symmetric under something called parity. That's just a fancy way of saying, if you took the entire universe, flipped it like a mirror image and watched it run, everything would work exactly the same. Left and right would be swapped, but otherwise, identical, fair, balanced. Except, what if it wasn't? This is where Li and Yang come in. They had this sneaking suspicion that the laws of physics, particularly those governing the weak nuclear force, the one responsible for radioactive decay, might be cheating. Maybe parity wasn't conserved after all, that they proposed an experiment, a bold one, but they didn't do it themselves. No, they handed the idea off like a hot potato to someone brave enough to actually test it. Chen-Shung Wu, a brilliant experimental physicist who, by the way, never got the Nobel for her role in proving this universe-breaking idea. She should have, but that's a whisper for another night. Wu cooled a sample of cobalt-60 atoms down to near absolute zero and put them in a magnetic field to line them all up. Then, she watched how the particles decayed. And what did she find? They preferred to shoot electrons in one direction, left, not random, not symmetrical, just left. The mirror shattered. That moment changed everything. Li and Yang got the Nobel Prize. The idea of perfect symmetry in the universe, gone, replaced by something far more intriguing and slightly creepy. The universe, it seemed, had a preferred direction, an opinion, a dominant hand. But if nature broke symmetry, something else could restore it, right? That's when the notion of mirror matter began to creep in. Maybe our universe isn't completely asymmetric after all. Maybe it's only half a picture. Maybe there's a second half tucked just out of reach, where everything is flipped, right where we are left, cold where we are hot, silent where we scream. In that mirrored universe, particles follow their own rules. Mirror protons, mirror electrons, mirror neutrinos, all behaving in ways that would restore parity if we could see the whole system. This isn't just idle speculation. The math checks out. Every known particle could, in theory, have a mirrored twin, and these twins would obey their own mirror versions of the same fundamental forces: mirror electromagnetism, mirror weak force, mirror gravity. But here's the twist. Except for gravity, these mirror forces wouldn't interact with ours. Their mirror light? It wouldn't illuminate anything in our world. Their mirror atoms? They'd pass through our walls like fog. You could have an entire mirror galaxy passing through your living room right now, and the only clue would be a slight gravitational tug on your floorboards, or maybe a creaky stair, or maybe that chill you keep blaming on drafty windows. And just like that, you've stepped into a universe where the familiar rules still apply, but only halfway. Historians still argue whether the concept of mirror matter took root directly from the fallout of parity violation, or whether it emerged later as a creative fix for other problems, like dark matter or neutrino anomalies. But either way, once that mirror cracked, physicists never stopped wondering what might be staring back through it. Here's a fringe gem for you. In the late 1950s, some physicists went so far as to suggest that mirror matter could be responsible for psychic phenomena, telepathy, ghosts, déjà vu, all chalked up to interactions with our mirror twins. It's not taken very seriously anymore, but it makes for excellent campfire talk and the occasional conspiracy-laced forum post from your uncle who refuses to get Wi-Fi. Still, the serious science marches on. The concept of mirror matter is tantalizing because it solves more than one puzzle. Not just symmetry, but maybe, just maybe, dark matter itself. So here you are, drifting in a universe that may be incomplete, like a book with half its pages printed in invisible ink. What would it take to read the whole thing? You imagine building a device that sees in mirror light. You'd hold it up and see glowing forms around you, cities, creatures, stars, all hidden in plain sight. But that's not how it works. Mirror photons don't interact with our detectors, our retinas, our cameras. They slip right through. The only way to feel their presence for now is through gravity, because mass bends space, no matter what it's made of. So if mirror matter is real, it leaves fingerprints on galaxies, motions, collisions. It nudges us, very softly, like a ghost that just wants to tap you on the shoulder. The birth of mirror matter, then, wasn't in some flashy lab or dramatic explosion. It was in a quiet realization that the universe has preferences, and those preferences suggest a missing piece. You snuggle deeper into your blanket now, the idea of a twin reality curling like steam into your thoughts. The symmetry we assumed for so long might be broken here, but somewhere, it still holds somewhere, the mirror hasn't shattered, and maybe, just maybe, it never will. You roll a little to your side, still floating gently through the haze of thought, and now your attention shifts to something deceptively simple. Your hands. You wiggle your left fingers, then your right. They feel the same, almost. But if you've ever tried to fit your left hand into a right-handed glove, you know the universe can be weirdly picky. Left and right are not interchangeable after all, and that little inconvenience is a big cosmic clue. Because when we talk about mirror matter, what we're really doing is picking a fight with the concept of parity. The idea that the universe should behave the same way whether you're watching it in a mirror or not. And sure, it usually does. Most of the time, left and right make no real difference. You spin a basketball clockwise or counterclockwise, it's still a basketball, but at the smallest scales the rules get weird. Nature, it turns out, does care which way something spins. A lot. You're now sinking into the strange world of subatomic behavior. Picture a particle, let's say a neutrino. It's moving forward at nearly the speed of light and it's spinning like a corkscrew. But which way is it spinning? That, dear listener, is everything. Physicists call this chirality, or handedness. Some particles are left-handed, some are right-handed, except in reality, only one kind tends to show up. In the case of neutrinos, only left-handed ones seem to exist. We keep looking for the right-handed versions, but they're like that one sock you can never find after laundry day, mysteriously absent, as if the universe itself has a favourite foot. And this favouritism is deeply unsettling. If the laws of physics are supposed to be symmetrical, then where's the matching half? Where are the right-handed neutrinos? Or more to the point, what if they exist but belong to a mirror universe entirely? This isn't just an idea people toss around for fun. It's a real tension in the standard model of physics, the best theory we have for explaining the zoo of particles that make up reality. The standard model works incredibly well, but it's lopsided when it comes to chirality. It violates parity. That's like building a perfect bridge that only goes east. So, to restore the balance, some theorists propose something wild. Maybe for every particle we can see, every electron, every quark, every neutrino, there's a mirror partner. Not just the same particle with a different name, but a truly mirrored version that obeys right-handed physics. A complete set, like a reflected chessboard with mirrored pieces following mirrored rules. Now here's where it gets even more unsettling. If this mirror sector exists, it doesn't just balance out the math, it might also explain why the universe is mostly made of matter, and not antimatter. That's been one of the biggest puzzles for decades. The Big Bang should have created equal amounts of matter and antimatter, which should have annihilated each other and left nothing behind except a very boring, very empty universe. But we're here, so clearly something tipped the scales. Mirror matter might be the missing part of that cosmic bookkeeping. Historians still argue whether this idea sprang up purely from mathematical necessity, or whether it grew organically from experiments in parity violation. Either way, the notion took root. If nature breaks symmetry here, it might restore it somewhere else. Here's a charming fringe tidbit to tuck into your sleep-deprived brain. In some speculative models, mirror matter might have mirror chemistry. That means mirror atoms, mirror molecules, and even mirror life could in theory form. You could have mirror DNA spiraling the other way, mirror trees growing downward, and mirror people brushing their mirror teeth with mirror minty paste. And if they ever figured out how to interact with us? Well, we'd be lucky if all they wanted was to borrow some sugar. But hold on, we're not there yet. Right now, you're lying in a universe that favours the left, with no obvious signs of its mirrored sibling. But the imbalance gnaws at us. We don't like our universe lopsided, so physicists have been dreaming up models where the two sectors, the visible and the mirror, are exact inverses, restoring the parity we lost when Chien-Shiung Wu froze cobalt atoms and broke the universe. In these models, mirror matter has all the same building blocks. Mirror protons and mirror electrons form mirror atoms. Those atoms could build mirror stars and mirror planets, but none of them would interact with regular photons. That's why we don't see them. Not because they're not there, but because we're blind to their kind of light. Imagine you're looking into a mirror. You wave your right hand and the reflection waves its left. But what if that reflection weren't just optical? What if it were physical? A real mirrored world right there on the other side of the glass, only you couldn't touch it, hear it, or see it with your regular senses. You might feel it though, ever so slightly, through gravity. There's a thought experiment you can try before falling asleep. Lie perfectly still and imagine that every particle in your body has a mirror twin doing the exact opposite motion at the exact opposite time. You sit up, it lies down. You raise your left hand, it raises its right. Somewhere out there, or maybe right here, your mirror self lives in a reversed reality, unaware of your existence. And maybe, just maybe, it's wondering the same thing about you. That's the strange magic of chirality. It's not just about which way something spins, it's about how deep a symmetry runs in the universe. The very laws that shape the atoms in your body seem to prefer one twist over another, one hand over the other, and that favoritism could be the fingerprint of something much bigger, hiding behind the scenes, a perfect twin world quietly doing everything in reverse. You're drifting now, but still aware. Somewhere in the distance, a tiny particle flips its spin, and a ripple passes into a world you cannot see, a world that might be your own, reflected and rearranged. You drift deeper now, past the familiar textures of space and time, down into the quieter corners of the 20th century. The coffee has gone cold in the break rooms of Columbia University. The blackboards are full of chalk scrawls, equations that seem to lurch sideways, like they're trying to slip out of the world they were born in. You're standing just behind two minds, Chen-Ning Yang and Tsung-Dao Li, as they tap at the fragile edges of reality. They're troubled. The math doesn't lie, but something's not right. The weak nuclear force, one of the four fundamental forces in nature, seems to be playing favourites, a violation they call it, parity violation. And it doesn't just make things messy, it makes things feel unfair. One side of the cosmic coin is heavier than the other. You remember this story from earlier, the cobalt-60 atoms, the bold experiment by Chien-Shiung Wu. You see it now in slow motion. Subatomic particles, tiny, aloof things, decaying ever so slightly to the left, always to the left. Never randomly, never fairly. It's like nature winks only one eye and the other's been sewn shut. When Wu's experiment confirmed that parity wasn't conserved in weak interactions, it shocked the scientific world. Not gently either. It was like someone had walked into a cathedral of symmetry and yanked the columns out physicists had been assuming for years that the laws of physics don't care whether you're left-handed or right-handed. And suddenly, oops, they absolutely do. But if you listen closely, behind all the headlines and Nobel Prizes, there was a second whisper. What if this broken symmetry wasn't a bug, but a clue? A clue that half the universe is missing. This is where the mirror universe creeps in, not as science fiction, but as a necessary fix. a restoration project. The idea was this: if the weak force violates parity by favouring left-handed particles, then maybe there's another set of particles, right-handed ones, out there, obeying their own mirrored version of the weak force. And maybe, just maybe, the two sectors don't talk to each other much. Maybe they're like awkward roommates sharing a studio apartment in different dimensions. This idea wasn't immediately embraced. Historians still argue whether the physics community took mirror matter seriously in the wake of Wu's experiment, or whether it stayed tucked away in fringe journals and footnotes, waiting for someone brave enough to take it dancing. But symmetry is seductive. It has a pull stronger than gravity, and physics, at its heart, loves a good balance. So the mirror world stayed alive, an elegant solution looking for a home. Imagine now you're standing on a beach at twilight. Waves are coming in from your left over and over, perfectly timed, never breaking from that rhythm. But what if, just over the horizon, there's another shoreline catching those same waves coming in from the right? You'd never see it, but the balance would be restored. That's what mirror matter offers, a hidden answer to a broken pattern. But the mirror world isn't just a hypothetical. The theory begins to flesh out. You start with particles, mirror electrons, mirror protons, mirror neutrinos. Not antimatter, this is key. Antimatter is just regular matter with opposite charge. Mirror matter is more profound. It's matter that obeys mirrored laws. The mirrored weak force doesn't just flip the charge, it flips the very interactions. In our world, particles decay to the left. In the mirror world, they decay to the right. A perfect cosmic balance, one side seen, one side hidden. And it gets weirder. The mirror universe would have mirror atoms, mirror chemistry, mirror stars fusing mirror hydrogen, mirror supernovas, mirror cats, though whether they're also in a mirror box is another paradox for another night. If this mirror matter exists, it doesn't interact with light as we know it. Our photons, the particles that carry light, have no reason to interact with mirror particles. They don't see each other. That's why we can't see mirror matter. But gravity is the gossip of the universe. It can't help but spread the news. If mirror stars exist, they'd bend space-time the same way regular stars do. Their presence could affect how galaxies spin, how clusters move, and that's where dark matter comes in. The galaxies in our universe spin too fast, as if there's extra invisible mass holding them together. Could that mass be mirror matter? That's the whisper growing louder in scientific circles. But even within that whisper, there's a tug of war. Some theorists argue that mirror matter could account for all dark matter. Others say it's too neat an answer, that mirror matter would interact just enough to leave hints we haven't seen. The debate is ongoing, still spiralling like a double helix in a mirrored test tube. Now here's your quirky tidbit of the night. There's a model out there that proposes entire mirror planets, including one that might be co-orbiting with Earth, forever hidden by the sun like a secret twin, sharing our orbit, always out of view. It's been suggested more than once in fringe astronomy papers, usually accompanied by diagrams drawn in Comic Sans. But who's to say? You're starting to feel the gentle disorientation now, like trying to walk through a funhouse where every mirror reflects something, just off enough to unsettle you. That's what mirror matter does. It's unsettling not because it's wrong, but because it feels so right. You start to see the pattern everywhere. For every imbalance, a counterbalance. For every particle decaying left, one decaying right. For every force that breaks symmetry, another one that mends it. And for every you, maybe another you. Not just a reflection, but a full living version built from mirror particles, following mirror physics, walking through a mirror world you'll never touch. The physicists didn't set out to find a hidden universe. They just noticed that something was missing from ours. And in the quiet that followed Wu's world-shaking experiment, someone dared to ask, what if we're only seeing half the picture? And so here we are, lying still in the soft dark, listening to the gentle rustle of mirror wings flapping somewhere just beyond the veil. A second universe, perfect in symmetry, gliding silently beside us, forever out of reach, unless, of course, you know where to knock. You're still lying there, half dreaming, half thinking, when a strange question begins to rise like fog in your mind. What would a mirror atom even look like? Could you hold it? Would it glow? Would it hum in your hand? Or would it slip right through your fingers like breath on a cold window pane? To imagine mirror matter, you have to start small. Think of a hydrogen atom, simple, reliable, the universe's favourite building block. One proton in the center, one electron orbiting around it. A neat little solar system, except everything is quantum and weird. Now reflect that hydrogen atom in a mirror. You'd get something that looks the same, but it's not just a flipped image, it's an entirely different thing, obeying flipped laws. In the mirror world, the electron is still negatively charged, and the proton is still positive. Unless, of course, the mirror universe flips charge conventions too, which some models suggest it does. Either way, mirror hydrogen behaves according to mirror electromagnetism. That's a whole other force. Identical in structure, but self-contained mirror electrons are pulled to mirror protons, and they stay within their own community. It's like living in a parallel town where everyone uses the same street names, but the roads never intersect. You roll over slightly and your bedsheets rustle like the whisper of particles interacting. Or not. In the visible world, atoms bump, collide, bounce. In the mirror world, they float past ours unnoticed. Your room could be filled with mirror air, mirror dust, even mirror spiders. Don't think about that too hard, and you'd never feel a thing. So what does it mean to build a mirror atom? You're building with the same architectural rules, but using invisible bricks. Mirror protons attract mirror electrons. Mirror neutrons do what they always do. Add mass, add stability. Put 3 mirror protons together and you've got mirror lithium. Combine mirror hydrogen and mirror oxygen. Mirror water. It's chemistry all over again. Just secluded. Now, a fun twist. Pun absolutely intended. In our universe, amino acids, the building blocks of life, are left-handed. Their mirror image versions exist called right-handed amino acids, but biology doesn't use them. Life here is picky like that. But in a mirror universe, everything could be reversed. Mirror life might be built entirely from right-handed amino acids, and not only that, it would be just as picky about its side of the symmetry line. That means mirror sushi, if it existed, would taste terrible. To you, at least. Because the molecules would be mirror-shaped, and your tongue wouldn't recognize them as edible. It's like trying to eat a key that almost fits the lock but twists the wrong way. You're grinning now, half asleep imagining Mirror MasterChef, and wondering if their judges complain about mirror salt being too mild. But back to atoms. Building mirror atoms is easy in theory. The hard part is figuring out how they'd behave on a larger scale. Could they clump into stars? Planets? Could they undergo fusion? Burn? Explode? The answer seems to be yes. If they're governed by the same physics, just mirrored, then everything our atoms do, theirs would too. With one major caveat. They don't mix. It's like 2 orchestras playing the same symphony in adjacent rooms, but with soundproof walls between them. You might feel the vibration of a timpani hit through the floor. That's gravity, but you'll never hear the melody. Historians still debate whether mirror atoms were first proposed as a way to restore symmetry for its own sake, or whether they came as a natural solution to the strange silence of dark matter. Either way, once you accept that particles can be mirrored, atoms become inevitable. And the fun doesn't stop there. Quirky tidbit of the night. There's actually a theoretical particle called the mirror photon. It behaves exactly like our photon, but it only talks to mirror-charged particles. If one passed through you right now, it would light up mirror matter but leave you totally in the dark. Quite literally. You could be bathed in a glow invisible to our eyes, surrounded by mirror light reflecting off mirror walls, and never know it. But what about touching it? What if you had a chunk of mirror matter in your hand? Well, first of all, you wouldn't be able to pick it up. It would fall through your fingers like it wasn't there, because the electromagnetic forces that make solid things feel solid wouldn't apply. That's right. Most of what we call touch is really just electric repulsion between atoms. Mirror atoms wouldn't repulse yours. They wouldn't see each other. They'd pass right through. But gravity might betray its presence. Put a chunk of mirror iron on a scale, and the scale would dip. It has mass. It warps space. It just doesn't care about your atoms. There's even a speculative idea that mirror matter could accumulate in Earth's core, dragged in over billions of years. That down beneath the crust, far below your feet, there might be little balls of mirror rock swirling around, undetectable but heavy. Maybe they even affect the way earthquakes happen. Maybe the Earth shivers sometimes, not from us, but from something we can't see, moving down there in the dark. You let that image settle into you like warm tea. A mirror world with mirror mountains, mirror rain, mirror volcanoes rumbling silently in a dimension we'll never reach. and all of it built from mirror atoms, stable, structured, isolated. There are, of course, rules. Not all physicists agree on how tightly coupled mirror matter would be to our universe. Some models allow for a tiny bit of kinetic mixing, a technical term for particles occasionally getting confused about which side they belong to. If that happens, it opens the door to wild possibilities, like particles flipping from our world to theirs, like neutron stars bleeding a little mass into mirror space, like mirror meteorites occasionally crossing over, visible only when they start to interact gravitationally. Imagine holding a piece of mirror metal that flickers in and out of existence, not because it's disappearing, but because it's phasing into a world where your eyes can't follow. You nestle deeper into your pillow thinking about the simplest things, atoms, charges, spins, and how they might be duplicated in silence, right here beside you. Mirror matter isn't magic. It's not supernatural. It's just very quiet, very shy, and very good at keeping secrets. But now that we've built the building blocks, mirror atoms, mirror light, mirror interactions, you're ready to start constructing something bigger. Stars, planets, maybe even cities, all made from matter that doesn't show up on any map. You're drifting now, not just through space, but through something quieter, stranger, an in-between place, a soft echo chamber where forces hum gently to themselves and rarely raise their voice. This is the realm of the dark sector, a whispered part of physics that's almost certainly real but endlessly elusive. Tonight your guide is gravity. It tugs you by the hand as you leave behind familiar forces like electromagnetism and the strong nuclear force. You're going somewhere more reserved, more secretive. A place where mirror matter might be not only hiding but flourishing. So far we've built mirror particles, mirror atoms, a ghostly kind of chemistry. But there's a missing piece you're just now beginning to sense: forces. Specifically, how do mirror particles interact with one another? Do they fight? Do they flirt? Do they form civilizations and quietly complain about how noisy our sector is? To answer that, you need to consider the idea of mirror forces. Just as we have electromagnetism in our universe, where electrons are drawn to protons, and light emerges from the motion of charged particles, mirror matter is thought to have its own version of that force, mirror electromagnetism. That's right. Not only are there mirror electrons and mirror protons, but they can also emit and absorb mirror photons. These mirror photons are completely invisible to us. They don't bounce off your eyes, don't trigger any of your instruments, and don't light up a room. But they're there, potentially flooding entire galaxies with mirror light. And it gets even weirder. The entire mirror sector may have its own version of all our forces, well, 3 out of 4 at least. Mirror electromagnetism, mirror weak force. Mirror strong force gravity, however, plays both sides. It doesn't discriminate. It's the nosy neighbour of the cosmos, always watching, always pulling, no matter where you come from. Now here's the thing. These mirror forces don't interact with ours. It's like 2 radio stations broadcasting on completely different frequencies. You could have a supernova going off in the mirror sector right next to you, and unless it pushes some gravitational waves into your detector, you'd never know. All of that physics, explosions, temperatures, radiation, goes on in total silence. But is it entirely silent? That's the question keeping physicists up at night while you're dozing comfortably through the fog of speculation. Some models suggest a possibility, a subtle one, that there's a faint link between the sectors. That's where the phrase kinetic mixing comes in again, like a soft static between those 2 radio stations. It's possible that mirror photons can mix ever so slightly with our photons. What would that look like? Well, it might mean that under just the right conditions, rare, finicky, borderline magical, a mirror particle might briefly interact with one of ours. A mirror electron might feel a tiny tug from a normal electromagnetic field. A mirror atom might scatter light just a little bit. But here's the kicker. It would be so faint that even our most sensitive instruments might mistake it for noise, or ignore it completely. Historians still argue whether early mentions of mirror electromagnetism were a direct response to the desire for symmetry, or whether they were added later to explain the growing unease around dark matter's cold silence. Either way, mirror forces allow for mirror matter to be a complete universe, not just a scattering of ghost particles, but a rich, evolving reality governed by its own laws. Quirky tidbit of the night. There's a very niche theory that posits mirror matter could be responsible for certain unexplained spacecraft anomalies. As probes drift through the solar system, some have experienced tiny, unexplained deviations in motion. A handful of theorists, not many but just enough to keep things spicy, suggest those deviations might be gravitational nudges from stray clouds of mirror particles. It's not the mainstream view, but it's one of those ideas that makes you raise an eyebrow and wonder, what if? So let's say mirror matter exists. It has its own particles, atoms and forces. What kind of world would that create? Start with stars. Mirror hydrogen and mirror helium would undergo fusion, just like in our sun. They'd burn mirror light, release mirror neutrinos, and eventually go supernova, spewing mirror elements into space. These would gather into planets, cool, rocky ones and gaseous giants, held together by mirror gravity, warmed by mirror starlight. Over time, you'd get mirror galaxies spinning in silent clusters, moving just as ours do, bound by the same gravitational rules. But unlike our galaxies, they'd never send light our way. You could look directly through one and never see it. Unless it passed through you. Yes, passed through. Because here's the thing. Mirror matter, since it doesn't interact with normal matter electromagnetically, doesn't collide with us in the traditional sense. Two clouds of mirror gas could drift right through the Earth with no resistance. You wouldn't feel a thing. Except, possibly, the Earth's gravitational field might wobble slightly. A nudge, a weight you didn't expect. And if mirror stars form, so can mirror black holes. In fact, some of the invisible objects we detect only by their gravitational effects might not be black holes at all, but clumps of mirror matter doing their own thing behind the cosmic curtain. Now close your eyes and picture this. A city, glowing in mirror light, orbiting a mirror sun. Towering structures made from mirror steel, roads paved with mirror concrete, people made from mirror carbon walking past mirror coffee shops. They don't see you. You don't see them. But gravitationally, you share the same flaw. If the two sectors are completely decoupled except for gravity, then they're like two ghosts haunting the same house, never touching, never speaking, but always pulling at the furniture just a bit. And if there is mixing, even the tiniest sliver, then maybe one day we'll learn to listen in. Maybe we'll tune our instruments to the right static and catch a whisper A signal, a sign that we are not the only inhabitants of our space. You turn in bed, the thought curling like smoke around your mind. Everything you see, everything you touch, might be just one half of what truly exists. The other half, a whole other set of stars, galaxies, and maybe stories, is unfolding in complete silence. And all it takes to miss it is being made from the wrong kind of matter. You drift now beyond Earth, past the rustle of the trees outside your window, beyond even the shimmering clouds of our own Milky Way. The universe opens like a soft, infinite curtain, star after star blinking in and out of view. But tonight, you're not here for the usual glitter. You're looking for the shadows, the weight, the parts that never light up but hold everything together with a silent, stubborn grip. This is where mirror matter and dark matter begin to blur into one another. You've probably heard of dark matter before. It's the cosmic heavyweight champion, completely invisible, totally silent, yet making up over 80% of the matter in the universe. It doesn't emit light, reflect light, or absorb it. It doesn't interact with the electromagnetic force at all, which makes it the ultimate party pooper at a photon rave. But it's real. We know it's there because galaxies spin too fast for their visible mass. Something unseen is keeping them from flying apart. Something is holding the stars in their orbits. You float now into a spiral galaxy, not unlike our own. It looks like a glowing pinwheel from afar, but when you peer into the data, the stars are moving in ways that defy explanation. The outer edges aren't slowing down like they should. They're whipping around as if clutched by invisible hands. Those hands, that's where dark matter lives. Or maybe, just maybe, where mirror matter hides. The idea has been around for a while that mirror matter, with its invisible atoms and self-contained mirror forces, could account for this missing mass. After all, it's made of particles. It has gravity. It clumps. It behaves like matter, just matter that we can't see. That's the dream scenario for physicists trying to tie up loose ends with something already lurking in the equations. And this isn't just a fringe idea tossed out after midnight at physics conferences. It's been seriously proposed that mirror matter could make up some, or even all, of the dark matter in the universe. It's elegant, it's symmetrical, it's spooky, but is it enough? You coast slowly through the data, observations from gravitational lensing, where light bends around invisible clumps of mass. In galaxy clusters, dark matter reveals itself by the way it distorts the space around it, not through sight, but through gravity's fingerprint. If mirror matter is out there, it would leave just such prints. Historians still argue whether the early mirror matter models were designed with dark matter in mind, or whether the overlap was a cosmic coincidence waiting to be noticed. But as dark matter continued refusing to show itself in direct detection experiments, mirror matter started to look less like a wild theory and more like a patient answer. Now, here's your fringe fact of the evening. In 2006, a group of researchers proposed that a cluster of mirror matter might have caused the Tunguska event, a massive explosion over Siberia in 1908 that flattened thousands of square kilometers of forest, yet left no crater or trace of impact debris. A mirror meteor, they said, would pass through Earth's atmosphere without glowing, possibly releasing energy through weak interactions or gravitational effects. It's a rare idea. But rare doesn't mean impossible, and it does make you look at the sky a little differently. You begin to wonder how many things have moved through us unnoticed. How many mirror stars have passed through the solar system, leaving only a soft tug on Saturn's rings or a slight nudge in a comet's path. And yet, as compelling as the mirror matter explanation is, it's not without debate. Some physicists argue that dark matter seems colder than mirror matter would likely be. Cold, in this context, doesn't mean temperature. It means slow-moving, clumpy, gravitationally focused mirror matter, with its internal mirror forces, could in theory form complex structures, mirror atoms, mirror gas clouds, even mirror stars, and these might not distribute themselves the same way as traditional cold dark matter. Others argue that mirror matter might clump too much. If it's forming mirror galaxies and mirror planets, then shouldn't we have seen some hint of it by now? Some gravitational disturbance that can't be explained by regular dark matter models? The rebuttal? Maybe we have seen it. We just didn't know what we were looking at. There are small gravitational anomalies in galactic behaviour, tiny misalignments between visible matter and inferred dark matter, that some suggest could be caused by structured mirror matter. Imagine mirror galaxies interleaved with ours, invisible but real, overlapping and interacting only through gravity. If that's true, then mirror matter isn't just a candidate for dark matter, it is dark matter, at least a good portion of it. It would mean that the invisible scaffolding of the cosmos isn't made of exotic particles no one's ever seen, but rather of a fully functioning shadow universe, one where stars rise and fall, where matter clumps and cools, where gravity reigns quietly just as it does here. You breathe slower now, letting the idea sink in. That every spinning galaxy, every gravitational wobble, might be caused not by strange, sterile particles, but by full systems, mirror solar systems, mirror moons, mirror meteor showers, arcing invisibly through our own. You picture a mirror Earth trailing beside ours in orbit, separated not by distance, but by interaction, just out of reach. A perfect twin, hiding behind a one-way mirror, following the same path around the sun, never seen, never heard, but always there. And in that universe, the dark matter problem is no mystery. It's just regular matter. You just don't belong to the right club to see it, so you tuck your head deeper into the pillow and let the weight of the cosmos settle in around you. You've crossed into a part of science that's neither proven nor denied, where experiments chase shadows and the truth may lie just a few microns to the left. Because if mirror matter is dark matter, then the universe isn't mostly empty. It's just hiding in reverse. You're floating now through a long, dim corridor lined with blinking lab equipment. The air buzzes, not with excitement, but with something quieter, heavier, hopeful disappointment maybe, or stubborn optimism. Welcome to the world of experiments, where mirror matter might have almost shown up but didn't. Or maybe it did. That's the trouble. You're in a particle physics lab now, somewhere underground. Could be Gran Sasso in Italy, could be a quiet wing at CERN. Wherever you are, it smells faintly of metal, coffee, and ambition. Scientists have been chasing whispers of mirror matter for decades, watching, waiting, tweaking settings in machines the size of cathedrals, all for a glimpse of something that might not even say hello. But let's start simple. One of the earliest ideas was to look for neutron disappearance. Picture this. You take a bunch of free neutrons, trap them in a bottle. Yes, that's a real thing. And watch how many remain after a certain time. Neutrons decay after about 15 minutes. But the thing is, we've got two ways to measure their lifespan, and they don't agree. In one method, you measure how many neutrons are still left in the bottle after a while. In the other, you count the number of decay products, like protons and electrons as they fly out. The two measurements are consistently off by about 9 seconds. Not 9 years, not 9 milliseconds, just 9 seconds. A small, stubborn difference. One theory, some neutrons might be vanishing, not by decaying, but by flipping into mirror neutrons. You don't see the decay products because there aren't any. The neutron just leaves, slips into the mirror world like it remembered it had somewhere better to be. And no, this isn't just wild speculation shouted over lunch. Some scientists actually set up experiments to test it. One team placed a magnetic field around their trapped neutrons and varied it slightly to see if it influenced the disappearance rate. In theory, if mirror neutrons exist, the magnetic fields of both universes might align at just the right setting, allowing some neutrons to oscillate into their mirror twins. The results? Inconclusive. Maybe there was something, maybe there was nothing. They couldn't be sure. Historians still debate whether this line of research gained traction because the evidence was compelling, or because the mirror matter hypothesis was too irresistible to ignore. Either way, it opened a curious new path. Not just mirror matter existing out in space, but interacting ever so slightly right here in the lab. Of course, it's not just neutrons. There have been attempts to detect mirror matter through orthopositronium decay. That's when an electron and a positron meet in a very specific way and form a short-lived exotic atom. Normally, this atom decays into photons, but under the mirror hypothesis there's a chance, tiny but possible, that it decays into mirror photons instead, which naturally we wouldn't see. The atom would vanish into invisible light. Several experiments have tried to detect this missing energy, looking for decays that should happen but seem to fall short. The results have been frustratingly ambiguous. Some teams report anomalies, others don't. The data shimmers like a heat mirage, maybe real, maybe just noise. You roll over slightly as if trying to make sense of the tangled wires of logic. These are real experiments, run by real people, spending years of their lives chasing an idea that never quite lands. It's like trying to catch a ghost in a butterfly net. And yet, the patterns are there. Every now and then, a detector blips. A signal appears where no signal should. A particle behaves just slightly off the script, like it's reading from the mirror version of the rules. Here's a charming fringe tidbit for the evening. In 1995, a group of physicists proposed that mirror matter might be responsible for ball lightning. That's right. Those glowing orbs that occasionally hover in storms, drift through walls and disappear. Completely unexplained by conventional physics, the idea? Maybe tiny pieces of mirror matter interacted with the atmosphere in just the right way to produce temporary glowing reactions, mirror fireballs if you will. Sounds far-fetched? Sure. But then again, so did quantum mechanics at first. There's also been interest in whether mirror matter could explain certain long-standing cosmic puzzles, like why some space probes, Pioneer 10 and 11 for instance, seemed to slow down ever so slightly as they left the solar system. A few speculative papers suggested this could be due to interactions with diffuse clouds of mirror matter in deep space. Most physicists lean toward thermal recoil explanations, but the mirror hypothesis lingers in the wings, tapping its fingers on the curtain. The frustrating thing is this. We've built the machines. Particle accelerators, underground detectors, magnetic traps, laser setups so precise they can measure the width of a human hair. From across a continent we've aimed them at every mystery the universe dares to throw at us. And still, mirror matter stays just out of reach. It's not for lack of trying, and it's just shy. Or maybe it's smart enough to know when it's being watched. You settle deeper under your blanket, thinking about the scientists who stare at screens for years, hoping for a single blip. The quiet hope that maybe, just maybe, a particle will zig when it's supposed to zag, and in that tiny zig we'll see proof of another world. A mirror world, ours flipped. Some experiments are still running, others have shut down, waiting for more funding, more sensitive instruments, or just a little more luck. There's talk now of sending new detectors into orbit, free from the noisy chatter of Earth, just to look for mirror interactions in space. Because here's the maddening truth. Mirror matter might be right here, around us, inside us, passing through us. And all it would take to see it is the right experiment, the right moment, the right mirror angle. But until then, we sit quietly, staring into the dark, asking the same quiet question. Did we just miss it? Again? You shift a little now, not quite awake, not quite dreaming, as something strange tickles the edges of your mind. Not a thought exactly, more like a question trying to climb out of the dark. What would it feel like to touch mirror matter? Could you shake a mirror hand? You're already floating in the logic of the impossible, so why not reach out a little further? Let's say you and your mirror twin are standing face to face, not metaphorically, but physically. Same size, same shape, same awkward smile. You both lift your right hand, their version lifts the left. You go in for a handshake, and your hands pass right through each other. No resistance, no impact, just nothing. Because here's the thing, the sensation of touch isn't some magic spell. It's all about electromagnetic repulsion. When you touch someone, or something, it's really your electrons repelling theirs. You never truly make contact. It's just two clouds of negative charge saying no thanks and pushing away. But mirror matter doesn't use our electromagnetism. It has its own, a mirror version. Your electrons can't see mirror electrons, so your hand would go through theirs like through empty space. It's disappointing, maybe. You imagine this dramatic moment finally meeting your mirror twin, and it's more like waving through a fog machine. But here's where things get weird again. Not everything is disconnected. Gravity, as always, refuses to mind its business. Mirror matter still has mass, which means it still exerts a gravitational pull. So if you were standing close enough to your mirror twin, you'd feel heavier, just slightly, like standing next to a dense object you can't see. Maybe a subtle lean in one direction, a shift in your balance. Your scales wouldn't lie, even if your eyes did, and the speculation doesn't stop there. Some physicists believe that under the right conditions, very rare, very delicate, there might be weak interactions between regular matter and mirror matter, not electromagnetic. Not strong or weak nuclear force, but something more exotic. Something that lets just a little communication slip through the cracks. One idea? Cooling. You see, mirror matter could potentially steal heat. That's right. It might act like a thermal ghost. If you had a chunk of mirror matter, somehow trapped in our world, it wouldn't radiate heat as we understand it. It wouldn't glow in infrared or warm your hand, but it would still vibrate with internal energy. And if it came into weak contact with your matter, it might slowly siphon off heat, quietly cooling the area around it. Imagine that. You reach toward an object and the air turns cold, not icy, just slightly off, like something's draining warmth, but you can't see what or where. Historians still argue whether this cooling idea originated from thermal models or if it was simply a convenient patch to explain some experimental anomalies, places where detectors seem to cool more than expected. But it sticks around because, well, it's eerie. And elegance aside, physics loves eerie things. Now here's your quirky fringe tidbit for the night. In 2003, a theory was floated that mirror matter might accumulate inside regular materials, not mix with them exactly, but lodge inside cracks or voids, trapped gravitationally. Like a splinter from another universe stuck in a piece of wood. The idea was that you might, just might, be able to capture mirror matter on Earth. You wouldn't see it, you couldn't touch it, but your instruments, if sensitive enough, might detect its mass or its cooling effect or its gentle gravitational nudge. And now your thoughts wander toward containment. Could you build a box that holds mirror matter? Well, yes, but only gravitationally. Regular containers wouldn't do anything. The mirror atoms would pass through the walls like mist, but gravity, that still works. You'd need something massive, like a deep potential well or a magnetic trap tuned just right to any tiny mixing effects. It's like trying to trap a shadow with a net made of silence. Still, if you managed it, you'd have the strangest object in the world. A box that weighs more than it should. Cold to the touch. Empty to the eye, but there. Pressing on the floor, dragging ever so slightly on nearby objects. A phantom with mass. You wonder, could that happen naturally? Some researchers think so. If mirror matter is floating around in the galaxy, pulled by gravity just like regular matter, then some of it might have already found its way to Earth. Not in large amounts, but tiny clumps. Maybe a mirror meteorite passed through the atmosphere, never lighting up, never burning, just sinking silently into the ocean or burying itself in a glacier, leaving no mark but a slightly heavier snowfall. You think now about shaking that mirror hand again, not in the physical sense, not bone to bone, but in a more poetic way. Could two people, one made of matter, one of mirror matter, ever know the other exists? The answer might be yes. If gravitational waves ripple from both worlds, if quantum particles occasionally leap between sectors, if cooling anomalies and neutron disappearances are more than just lab quirks, then maybe, just maybe, that handshake isn't physical. It's a recognition, a wave across dimensions, a mutual tug in the dark. Because sometimes, all it takes to know something is there, is the way it makes you move. You lie still now, imagining a mirror city rising in the same space as yours, buildings stacked like ghosts on top of your walls, a mirror cat sitting on your mirror desk, mirror people watching mirror stars, all weightless, invisible, but real. And maybe one of them pauses, feels a soft tug downward, and wonders, was that you? You drift upward now, rising past rooftops and city lights, past the cloud cover and cruising aircraft, until the sky folds open into stars again. But this time, you're not looking at the ones you know. Not our brilliant burning suns, not the galaxies painted in infrared and ultraviolet. Tonight you're gliding into something altogether darker, colder, stranger. Tonight, you wander among mirror stars. You've been here before, in concept, mirror atoms, mirror forces, mirror matter. But this is where those ideas scale up, where particles become planets, and physics becomes architecture. Because if mirror matter behaves like regular matter, just shy and non-interacting, then it shouldn't stop at forming atoms. It should go all the way. And the universe doesn't like to waste building materials. So now you're gliding through space alongside a mirror galaxy, composed entirely of stars that never shine for you. They burn, but only in mirror light. They pull, but only through gravity. From a distance, their presence is betrayed by how visible galaxies twist and tumble around them, like wind moving through trees you can't see. You float beside a mirror star now. It's massive, 10 times the size of our sun, but it emits no visible light, no ultraviolet, no warmth. Yet you feel its weight, its gravitational hum, a silent thrum in the fabric of space. It fuses mirror hydrogen into mirror helium, same as our stars do, but it does so in complete seclusion, a campfire in a locked room. How many of these stars might exist? It's a question that drives entire subfields of astrophysics. We know dark matter forms halos around galaxies, invisible spheres that keep the stars bound together. But what if, instead of some exotic dark particle, those halos are actually clusters of mirror galaxies, mirroring our structures, overlapping our own, their shapes unseen but their mass undeniable? It would mean that every galaxy we observe could have a hidden twin, an invisible spiral riding alongside ours, dense with its own stars, its own planets, maybe even its own black holes. Historians still argue whether this idea first came from attempts to explain galaxy rotation curves or from earlier mathematical models built purely for symmetry. But either way, the concept grew. If mirror matter exists and it behaves the same way, then structures must form. Stars would be born the same way, clumps of mirror gas collapsing under gravity, heating up, igniting mirror nuclear fusion. Their life cycles would mirror ours too, main sequence, red giant, supernova. But their light, their heat, their radiation, all invisible to us, unless we catch their gravitational signature, and we have. Astronomers have found stars that wobble for no visible reason, objects that orbit nothing we can see, micro-lensing events where something passes in front of a distant star and bends its light, yet leaves no trace. Some of these might be black holes, sure, but some might be massive clumps of mirror matter intervening silently. Your quirky tidbit tonight? In 2018, a small group of astrophysicists proposed that some isolated neutron stars, those out in space with no visible companion, might actually have mirror star partners. They'd be part of a binary system, but only one half would shine in our sky. The other half would be tugging invisibly, pulling the visible star in a wobbling dance only precise instruments can detect. Imagine a mirror sun rising in a mirror sky, warming mirror planets, maybe even supporting mirror biology, and all of it utterly invisible to our telescopes. You could point the Hubble straight at it, and it would show you a field of stars with nothing remarkable. But in the background, hidden behind the veil, an entire stellar civilization could be burning. Let's go one step further. If mirror stars exist, then so do mirror galaxies. And these wouldn't just be faint clouds. They could be fully structured systems, orbiting each other, forming spiral arms, merging, colliding galactic ballet performed in absolute darkness. You ease through one now, not with sight, but with imagined senses, a swirl of mass flowing and rippling bound together by mirror gravity. No light, no radiation, just motion, silent and massive and elegant. And if there are galaxies, then there could be clusters. The large-scale structure of the universe, the cosmic web, is built from tendrils of dark matter. It's what gives our visible universe its shape. Mirror matter could be riding those same filaments, clinging to the same gravitational scaffolding, forming a shadow web that mimics our own. It's a cosmic hall of mirrors with no glass. You might wonder, if they're so real, so massive, why haven't we crashed into one? But remember, mirror matter doesn't interact with us through normal forces. If our solar system passed directly through a mirror gas cloud, we'd feel only the gravity. Our planets might wobble, our comets might shift course, but we'd see nothing. We'd feel nothing on our skin. And if we passed near a mirror star, it would be like sailing past a lighthouse that shines only in another spectrum, its light blazing for mirror eyes alone, while we remain completely unaware. And yes, mirror black holes would form too. A mirror star reaches the end of its life, collapses, and tears through the fabric of mirror space-time, forming a singularity that pulls on everything near it, even our matter. Because gravity, always the gossip, crosses party lines. Some black holes we detect could be entirely dark, not because light can't escape, but because there never was light to begin with, just mass, just pressure, just pull. You settle deeper into your blanket, the idea washing over you like cool water, that most of the universe may be illuminated only in a kind of light we'll never see, that between every visible galaxy lies a mirrored one keeping pace, holding hands with ours across a divide thinner than thought. And you're part of one side, but you might just feel the other, tugging on your orbit, whispering through the stars, existing not in opposition, but in balance. A universe with a twin, a galaxy with a ghost, a cosmos built in double. You float now through the deepest silence, where even gravity holds its breath. The galaxies have thinned out, and the stars have faded behind you. You're not in space exactly, you're in possibility. In the pale space between science and dreaming, and there, nestled within the folds of maybe, one idea curls itself around your mind like a cat warming your feet. What if there's another Earth? Not another planet, there are plenty of those, but a true twin, a mirror Earth. Imagine it, same size, same orbit, same atmospheric density, a world made of mirror matter, right here in our solar system, yet totally invisible to us. It wouldn't reflect sunlight, it wouldn't block the stars, it wouldn't even cast a shadow, but it would exist, solid, real, and maybe, just maybe, inhabited. You let the image settle in, a planet spinning silently beside us, made of mirror atoms, orbiting a mirror sun, trees made of mirror cellulose, oceans of mirror water, life built from right-handed amino acids, breathing mirror air under mirror skies. And now the question sharpens, the way questions sometimes do at the edge of sleep. Could there be mirror life? Not just particles, not just physics, but people. Let's back up. First, mirror chemistry works. We've already drifted through that. Mirror hydrogen, mirror oxygen, mirror carbon. If you've got atoms, you've got molecules. And if you've got molecules, biology becomes possible. Now consider this. Our biology is based on an extreme preference. Life on Earth only uses left-handed amino acids and right-handed sugars. Flip the chirality, and our enzymes go on strike. Your body would treat a right-handed amino acid like a foreign object, or worse, as nothing at all. But a mirror universe wouldn't think twice. There, right-handed amino acids are the norm. Mirror DNA spirals in the opposite direction. The building blocks of life stack up in symmetrical opposite fashion. There's no reason, none, really, that life couldn't evolve on that side too. Historians still debate whether mirror life was taken seriously when the theory of mirror matter first emerged, or if it was quietly tacked on later by the kind of scientists who get nervous when their equations start looking too lonely. But slowly, the idea gained traction. If a parallel universe could mirror our physics, why not our biology? Let that settle in. You're not alone in the universe, perhaps not even in your own bedroom, because if mirror life exists, then it's not out there in the way alien life might be, it's right here, sharing your space. But never sharing your light. You could have a mirror neighbour, mirror cities, mirror oceans sloshing under mirror hurricanes, whole ecosystems just offset enough to be entirely invisible. You wouldn't hear the thunder, you wouldn't feel the rain. But if a storm passed close enough, you might feel the pressure drop. You might feel your own world tug a little toward a cyclone you can't see. And maybe these mirror life forms, wonder about you too. Maybe they have their own scientists, mirror telescopes, mirror physicists debating the strange gravitational anomalies in their stars. Maybe they have a dark matter problem, and you are it. You roll slowly in bed, the thought curling tighter. Could a mirror version of you exist? Not metaphorically, not just a poetic reflection of your soul, but a biological atomic twin, made of mirror matter, shaped by mirror evolution. With your habits, your voice, your sleepy eyes, just flipped. And now the idea stings, just a little, because it forces a strange intimacy. You're no longer the only you. There could be another, made from the opposite side of nature's symmetry, living a life that echoes yours in reverse eating breakfast while you eat dinner, turning right when you turn left, waking up with the same sense of quiet confusion on a different kind of Tuesday. Of course, the scientists will caution, we have no evidence of mirror life, no signals, no mirror SETI, no signs scratched into the stars. But then again, how would we know? If mirror matter doesn't emit or absorb our light, no optical telescope could catch it. If mirror radio waves don't interact with our electronics, we'd never receive their broadcasts. We'd be like fish in a pond wondering if there's anything beyond the water, listening for sounds that don't travel through our medium. There's even a fringe theory, here's your odd little fact tonight, that some unexplained UFO sightings might be mirror objects temporarily interacting with our world. Not spaceships from another star, but vehicles from the mirror sector briefly breaching the boundary. The idea pops up now and then in papers too bold for Nature, too weird for the New York Times, but it lingers, because it scratches at something that feels plausible in the bones. You imagine two worlds now, overlapping but estranged. Mirror Earth orbiting alongside us, tucked into our solar system like a perfectly choreographed dance partner. Maybe it hides behind the sun, always just out of sight. Maybe it's here, occupying the same space but sliding between dimensions like a shadow cast in a light you can't produce. Could we ever interact? Could we ever shake that mirror hand? Well, maybe. If tiny mixing effects exist, if mirror photons flirt with our photons just a little, there could be ways to communicate. Mirror matter might occasionally produce a signal we can detect. However faint, a mirror civilization might one day build instruments that talk through the thinnest crack in the wall. And what would we say? Hello, neighbour. Or maybe just a soft knock, a tap, a blink of light. You lie still now, aware of how much empty space surrounds you. A whole universe between you and the next person over. And perhaps another universe layered on top of that full, crowded, whispering. If mirror life exists, it doesn't want to be seen. Or maybe it can't be. But it's there, breathing mirror air, writing mirror songs, falling in mirror love. And just maybe they're lying in bed too, wondering about you. You lie there now, wrapped in the quiet hum of your room, when suddenly something flips. Not in your head, this is subtler than that. It's the whisper of a neutron, one of the most ordinary particles in your body doing something very unordinary, disappearing. And not just disappearing into nothing, disappearing somewhere. You're about to ease into one of the strangest corners of the mirror matter mystery, quantum portals and neutron leaks. Yes, that's a real phrase. Let's rewind a little. You already know that neutrons, when free from atomic nuclei, decay after around 15 minutes. It's been measured over and over, but what's less known outside of physics circles is that how you measure it affects the answer. Bottle experiments, where neutrons are trapped and counted directly, give one lifetime beam experiments, where you watch their decay products give another. The two numbers should match. They don't. Not quite. There's a stubborn discrepancy. A few seconds, small enough to ignore if you're the kind of person who ignores reality leaking through cracks. But physicists aren't wired that way. They want answers. Why are these neutrons vanishing more quickly in bottles than in beams? Enter the idea of neutron mirror neutron oscillation. What if, under the right conditions, a neutron can flip into a mirror neutron? Not decay, not explode, just switch sides. One moment, it's here in our world. The next, it's phased into the mirror sector where it continues existing, but obeys mirror rules. It's not just speculation, it's being tested. In carefully controlled labs, scientists set up magnetic fields around neutron traps. Why? Because if the two sectors, our world and the mirror world, have similar magnetic field strengths, it might allow for resonance, a point where a neutron could flip dimensions like a tuning fork hitting just the right note. The results? So far, ambiguous. Some experiments hint at subtle deviations when magnetic fields are adjusted just so. A tiny change in the neutron survival rate. Nothing dramatic, no neutron goes poof with flare, but something that makes the physicists raise their eyebrows and scribble a lot in notebooks. And here's where your room starts to feel less isolated. Because if neutrons can occasionally flip into mirror neutrons, then it's not just theory anymore, it's interaction. It's a form of communication. A whisper across universes, not of language or thought, but of matter itself. It means our world leaks, ever so slightly, and that changes everything. It suggests that under just the right circumstances, say, in high-energy environments or intense magnetic fields, particles might slip between realities, that the boundary between our universe and the mirror one is thin, porous, flexible. Think about what that means for a moment. A neutron in a distant star might vanish, not due to decay, but because it's been tugged across into the mirror world, and mirror neutrons might do the same in reverse. It creates the possibility of quantum portals, not with blinking wormholes or glowing CGI spirals, but with subtle, invisible passages. A neutron here, a neutron there, a balance maintained like a cosmic seesaw. Historians still argue whether the concept of neutron mirror neutron oscillation emerged purely to explain experimental discrepancies, or if it was always lurking in the background of mirror matter theories. Either way, it's one of the most promising bridges between us and them. Here's your quirky fact of the night. In 2020, a new experiment was proposed to send ultra-cold neutrons through a long magnetic tunnel. One where the magnetic field could be finely tuned to match a hypothetical mirror field, the idea. Catch a neutron not arriving at the end, not decayed, not stuck, just missing. The scientific equivalent of calling someone's name and hearing no echo. And if mirror matter has mass, and mirror gravity, and mirror chemistry, then it's hard not to wonder what a neutron does once it gets there. Does it immediately bind into a mirror nucleus, float freely through mirror space, bump into mirror scientists who are also baffled by a neutron that came out of nowhere? You roll that idea around in your mind like a marble. Two universes, connected not by wormholes, but by resonance. Two worlds, tied together by occasional leaks of mass. And if neutrons can do it, why not other particles? Electrons, perhaps, or atoms under extreme conditions. What about quantum tunneling events where matter briefly crosses into the mirror world, then returns slightly changed, its energy tweaked, its spin reversed? Could this explain some of the more puzzling results in particle physics? It's a slippery slope, but one that many physicists are now eyeing with curiosity rather than scorn. You imagine a high-energy collider somewhere deep underground, hurling particles at each other. Most of the debris flies out in predictable showers, but every so often a particle vanishes, mid-flight, mid-decay. Not accounted for, not part of the final math. Maybe it didn't disobey the rules. Maybe it just changed which rulebook it was following. This opens the door to an even wilder idea. Could we someday build a mirror portal? Not to walk through, not for some interdimensional handshake, but for communication. If we could control the flipping of neutrons, turn it on and off with field tuning or resonance shifts, could we send encoded signals? Could we modulate the rate of oscillation and use it to convey information? What if we already are? What if somewhere deep in a mirror lab someone is sending mirror neutrons our way? A kind of Morse code, not in dots and dashes, but in disappearances and arrivals. Of course we have no way to read it, not yet, but you lie back now, your thoughts layered like soft linen sheets. On the top, your world. below it, something darker, something cooler, not sinister, just quiet mirror Earth, mirror physics, mirror stars, and here, in the space between, a few particles moving from one to the other, like letters slipped between apartment doors. It means we're not fully sealed off from our twin universe. There's a leak in the wall, a very small one, but it's there. And maybe, just maybe, that's the first step toward listening. You drift now through equations, not stars, through the soft rustle of paper, not particles. The air feels drier here. Static clings to the edge of your thoughts, because this is the realm of pure theory, and in this place, beauty matters. Tonight you're settling into the math that whispers mirror matter into being, because for all the experiments, all the speculations, all the far-off galaxies and vanished neutrons, mirror matter has always had one stubborn ally on its side: symmetry. That quiet, elegant feature of the universe that shows up in everything from snowflakes to equations to the face you see in the mirror. You're going to glide through this gently, no math degree required. You won't be solving anything tonight, just following the shapes. It begins with the simple idea: the laws of physics should work the same way everywhere. Flip a system left to right, or run it backward, or shift it in space, and the rules shouldn't change. This is the foundation of symmetry in physics, and it's given us some of our most powerful tools. Noether's theorem, for example, a lovely bit of mathematics from 1918, says that every symmetry in physics corresponds to a conservation law. Time symmetry, conservation of energy. Spatial symmetry, conservation of momentum. These ideas aren't just philosophical, they're woven into the rules of everything. But then came the wrinkle. You remember this: the discovery that the weak nuclear force violates parity, that it prefers left-handedness, that the universe doesn't treat left and right the same. It was a devastating blow to the dream of perfect symmetry. Unless you restore it another way. What if the universe as a whole still respects parity, but only when you include a hidden mirror sector? One where all the left-handed particles in our world have right-handed twins, where all the violations here are balanced by corresponding ones there. And the math, it loves that. You're now wading into a model called the mirror world model. It's not fantasy, it's a legitimate extension of the standard model of particle physics. You start with all the particles we know: quarks, leptons, bosons, then you duplicate them. For every familiar electron you introduce a mirror electron, every up quark gets a mirror up quark, and so on. But the important part isn't the duplication, it's the separation. These mirror particles don't interact with our particles via the strong, weak, or electromagnetic forces. Only gravity. Maybe the tiniest whisper of mixing through hypothetical portals, but otherwise, two full sets of particles, two sets of forces, two linked but lonely universes. And it works. The equations balance, the symmetries hold. It's like solving a puzzle that never quite made sense before, until you realize the other half was behind the couch the whole time. Physicists call this parity symmetry restoration, and it's one of the strongest theoretical arguments in favor of mirror matter. It's not there to explain an anomaly, it's not a desperate patch, it's an aesthetic fix. And in physics, that's more powerful than it sounds. Because the universe, oddly enough, tends to like elegant math. Of course, not everyone agrees. Historians still debate whether the push for symmetry is a bias of human brains rather than the cosmos itself. After all, we like balance, we crave it, we find beauty in it. But is that a reflection of reality, or just of us? Some physicists worry that mirror matter is too convenient, that it solves problems we don't fully understand yet with answers we can't test, that we're chasing elegance instead of evidence. But others argue the opposite, that the mirror world is an inevitable consequence of our own assumptions, that once parity was broken, a full mirror sector became not an optional add-on, but the most natural way to restore the deeper order. Here's a quirky tidbit you'll enjoy. In some extended mirror models, even the Higgs boson has a mirror twin. The so-called mirror Higgs would help mirror particles acquire mass in their own sector. And just like our Higgs field fills all of space, so would theirs. It's a twin fog we'll never walk through, but it shapes everything on that side. And there's more. Supersymmetry, another elegant theoretical extension, can also be combined with mirror models. String theory? Yep, it's got room for mirrors too. Even certain versions of brain-world cosmology allow for our universe and its mirror sibling to exist on adjacent branes in a higher dimensional space, like two pieces of toast sliding past each other in a cosmic toaster. You smile, half dreaming, imagining theoretical physicists sipping cold coffee, arguing over whether our toast is butter side up. And maybe the most poetic possibility of all, that our universe and the Mirror One were born together, not as two accidents, but as one necessity, one bang, two worlds, one symmetric explosion, two asymmetrical results that, when taken together, restore the balance, a cosmic yin and yang, a pair of quantum footprints walking away from the same origin in opposite directions. You breathe slower now, because here's what this all means. The case for mirror matter isn't just built on anomalies or speculation or missing mass. It's built on the idea that the universe likes its books balanced, that somewhere out there, or in here, are the missing entries. A whole other ledger written in invisible ink but with every column aligned. And maybe we'll never see it directly. Maybe no experiment will ever catch the mirror photon, or trap the mirror neutron, or decode the mirror message. But the equations, those quiet, careful scribbles etched into blackboards and notebooks, they see it. And in the silence of theoretical physics, where beauty and truth sometimes hold hands, that's often enough. You let the thought fade like chalk dust. Let the math drift off the page, and you too begin to slip gently downward. Softly now we slow, drifting, folding the edges of the mirror closed, and letting the symmetry settle, like dust, on twin universes. The night is softer now. You've wandered through galaxies that glow in silence, stood beside stars that shine in invisible light, and imagined cities that rise in the shadow of ours, untouchable, unknowable, but no less real. You've followed neutrons slipping between dimensions, traced the outline of symmetry in the laws of physics, and asked questions that may never have answers. And yet, they mattered. They filled the quiet space between sleep and waking with the shimmer of what might be. Because in this vast, sprawling universe, so rich in wonder, so careful with its mysteries, maybe it's okay not to know everything. Maybe the beauty is in the not quite yet in the possibility, in the mirror half of the story. So let your breathing slow now. Let your thoughts dissolve like particles into quiet space. The stars can spin without you for a while. The equations can rest. You've earned your place in the silence between worlds. And whatever is out there, whoever, is dreaming too. You're deeper now, somewhere between REM sleep and the cosmos, wrapped in the warm haze of uncertainty. You've wandered through symmetrical equations, balanced particles, and mirrored forces. And yet, despite all that elegance, one nagging question still floats stubbornly in the back of your mind like a single sock that escaped the laundry. Why can't we see it? If mirror matter exists, if it's real, structured, and fills the universe like scaffolding, then why is it still so impossibly invisible? Why does it stay hidden, tucked into gravity's folds, refusing to shine, reflect, or so much as wink in our direction? Tonight you're going to follow that question like a trail of breadcrumbs. And yes, the trail leads into a dark forest, one with no visible trees. Let's start with the obvious. Mirror matter doesn't interact with light. That's the core of its invisibility. It has mirror photons, which only talk to mirror-charged particles. Our photons, the ones bouncing around your room, bouncing off this sentence, bouncing off the moon, simply don't know mirror matter is there. It's not that mirror objects are transparent. It's that they're undetectable in any traditional electromagnetic sense. A mirror table would cast no shadow. A mirror sun would offer no warmth. Even a mirror elephant doing cartwheels in your living room wouldn't nudge a single photon your way. So what does that leave us? Gravity. The one universal translator. The one force that doesn't care what you're made of. If you've got mass, you warp space-time. Period. That's why we suspect mirror matter exists in the first place. Not because we've seen it, but because of the way things move. Galaxies spinning too fast, lensing events with no visible cause, structures forming earlier than they should have, as though guided by invisible hands. But that's indirect. A shadow of a shadow. It's like trying to prove your roommate exists based only on the fact that your cereal keeps disappearing. You shift under your blanket, still pondering. Could we ever detect mirror matter directly? Well, maybe. There are theoretical windows, cracks in the wall between sectors. You've already floated through one, kinetic mixing, a tiny bit of coupling between our photons and mirror photons. If that mixing is real, then in extremely rare cases mirror matter might scatter our light, weakly, indistinctly, like headlights catching the outline of fog. Some experiments, deep underground ones with names like DAMA/LIBRA and COGENT, have reported unusual seasonal variations in signal strength. The idea is this: if Earth moves through a cloud of mirror matter as it orbits the Sun, we might see tiny fluctuations in dark matter detection rates, not proof, not even a firm handshake, but a shrug from the other side. And yet, the results are messy. Some detectors see a hint of something, others don't. Historians still argue whether this inconsistency is due to different materials, experimental noise, or something far weirder, like mirror matter only interacting with certain atomic nuclei under specific conditions. The truth, we don't know, not yet. Another challenge is that mirror matter doesn't clump quite like regular matter. It forms stars, yes, and galaxies. But without interaction with regular light, it doesn't cool and collapse as easily. That means fewer compact mirror objects in our neighbourhood, fewer chances to bump into one, fewer cosmic near misses with mirror asteroids or stray mirror pets. And yet, maybe we have seen it and just didn't know what we were looking at. Here's a delightfully odd little tidbit. Some of the ancient impact craters on Earth, like the one in Siberia's Podkamennaya-Tunguska River area, show signs of massive explosions. Without any impact debris, no meteor, no metal, just flattened trees and scorched earth. Could it have been a mirror meteor, slipping through our atmosphere mostly unseen, heating up just enough through kinetic mixing to explode, then vanishing back into quiet? Fringe idea? Yes. But it's one of the more charming ones. Another theory suggests that mirror matter could be hiding in plain sight, but only as an undetectable addition to known masses. Say, for instance, there's a strange gravitational anomaly in the orbit of a satellite. One explanation: the satellite's moving strangely. Another: there's a pocket of invisible mass nearby, mirror matter embedded in Earth itself. Some scientists have proposed mirror iron hiding deep within the planet's crust, subtly pulling on nearby objects, never lighting up. Again, no proof. But the idea refuses to leave. So why can't we see mirror matter? Because everything we've ever invented, our telescopes, our sensors, our brains, evolved to interact with our forces, our photons, our chemistry. We built our tools from the universe we know, but mirror matter doesn't live in that universe, not in full. You can't see it because you were never meant to, and yet you do feel it. Every time a galaxy spins too fast, every time light bends without cause, every time a detector pings with no clear particle trail, it's like standing in a dark room and sensing someone's presence behind you. You don't see them, you don't hear them, but you know they're there. Gravity taps you on the shoulder, and the hairs on your neck do the rest. So maybe the question isn't why can't we see it, but why do we keep trying? The answer is simple: because the universe is incomplete without it. We see only a fraction of what must be, and that bothers us. It's the kind of itch you can't scratch. The kind that gets scientists out of bed in the middle of the night to check data sets for anomalies that might just be noise. You roll gently in bed now, drifting towards sleep, and just before your mind lets go completely, you feel it. That tug. Not of gravity, but of possibility that something is near. Something real. Something hiding. Not out of malice. Not out of mystery, but because it was never built to glow. You're resting now, deeply tucked into the folds of thought, and yet your mind keeps drifting back to the edge of the dark, where mirror matter waits, where shadows have mass, where silence has gravity. But tonight, you're not just cuddling up with the idea of mirror matter, you're putting it in the ring. Because as elegant as it is, mirror matter isn't the only theory trying to explain the cosmic mystery of dark matter. Nope. The universe has options, and now, like some theoretical reality show, you're about to weigh the contestants. Welcome to mirror matter versus the other dark matter theories, because the universe might be strange, but it's not short on imagination. Let's start with the reigning favourite among many physicists for decades, WIMPs, weakly interacting massive particles. They're classic, clean predictable. WIMPs are theoretical particles that have mass, like mirror matter, but interact only via gravity, and possibly the weak nuclear force. If they exist, they'd be everywhere, ghosting through your body by the billions every second, never touching, never saying hi. They're popular because WIMPs fall out of certain extensions to the standard model like supersymmetry. They also behave beautifully in simulations. They clump. They help galaxies form. They explain the cosmic microwave background patterns. What's not to like? Well, the whole not showing up in any experiment ever thing. Despite decades of trying, we haven't found a single WIMP. Not at CERN, not deep underground, not in outer space. It's starting to feel like waiting for a bus that got lost in another dimension. You shift slightly. This is where mirror matter steps forward, clears its throat and says, "Hey, maybe I was the bus all along." Unlike WIMPs, mirror matter isn't a totally new kind of particle. It's a mirror version of what we already know. The same zoo of electrons, protons and neutrons, but flipped, segregated and shy, that makes it feel familiar. Elegant. Less like inventing a new puzzle piece, more like finally flipping the one you've had upside down. But there's a catch. Mirror matter is a full sector. It's not just one particle. It's an entire mirrored standard model. That's a lot to swallow. An entire invisible copy of reality, with its own galaxies, its own chemistry, and possibly its own life. It's a bold claim. That brings us to the next contender, axions. These are tiny, hypothetical particles that were originally invented to solve a completely unrelated mystery, the strong CP problem in quantum chromodynamics. But axions turned out to have another trick. They make great dark matter. They're super light, super abundant, and like mirror matter, they don't interact with light. But unlike mirror matter, they're boring. No chemistry, no stars, no cities, just a cosmic fog of cold, quiet particles filling the universe like an invisible wind. If mirror matter is a whole hidden civilization, axions are tumbleweeds. Still, they're a strong candidate. There are axion detection experiments underway right now, including clever ideas using resonant cavities, magnetic fields, and even dying stars. And if they're found, they could not only solve dark matter, but fix other pieces of the standard model in one swoop. And then, over in the corner, there's a less mainstream, yet still intriguing theory, modified gravity, or MOND, modified Newtonian dynamics. This one says, maybe there's no dark matter. Maybe gravity just behaves differently at large scales than we expect. Sounds appealing, right? Unfortunately, MOND tends to struggle when you move from individual galaxies to large-scale structures. It explains some rotation curves beautifully, but falls apart when you get to galaxy clusters or the cosmic web, and it doesn't play nice with gravitational lensing data. Still, it lingers, because the idea that we misunderstood gravity, that maybe Newton and Einstein only got it mostly right, has a certain poetic charm. But for now, most physicists lean toward the missing mass explanation. And if we return to missing mass, mirror matter stands out for a very specific reason. It has structure. WIMPs and axions are both inert. They don't clump into atoms or planets, but mirror matter can. That means it could form mirror stars, mirror galaxies, and explain gravitational anomalies that go beyond just mass. It could explain patterns, alignments, maybe even interaction events. One such example: colliding galaxy clusters like the Bullet cluster, where normal matter and dark matter appear to separate after the collision. Some say this supports WIMPs. Others argue that mirror matter could behave similarly, especially if it has its own complex dynamics. Historians still argue whether the shift toward mirror matter was driven by the elegance of parity restoration or the growing fatigue over WIMPs dodging every experimental net. But the result is the same. Mirror matter is no longer the underdog. It's a serious structure-rich contender with growing theoretical momentum. Here's your fringe fact of the night. There's even a theory suggesting that dark atoms, bound states of dark protons and dark electrons, mirror or otherwise, could exist with their own periodic table. Not just carbon and hydrogen analogues, but whole families of elements with unique dark chemistry. We wouldn't see them. But in their own spectrum, who knows what kind of molecules they've built? You smile, imagining a mirror Mendeleev arranging his mirror table of mirror elements in a dusty mirror lab, frowning at an isotope that refuses to behave. It's easy to fall in love with mirror matter. It's just weird enough to be compelling, just familiar enough to feel possible. It's more than a fix, it's a full-on second reality. But WIMPs and axions still have loyal fans. They're simpler, cleaner, less existential. Because let's be honest, It's one thing to believe in a ghostly particle, it's another to believe in a ghost universe. And so the debate continues. In labs, in journals, in quiet minds lying awake like yours, each theory sitting with its hands folded, waiting for the next piece of evidence to arrive, waiting for one glimmer of something that doesn't belong, waiting to be seen. You're dreaming now, but not the kind with melting clocks or flying teeth. No, this is the kind of dream built from probability and theory, stitched together by late-night speculation and a quiet need to connect. And tonight, your question floats softly above the rest. Could mirror life ever talk to us? Not just exist, not just drift silently through its own mirror world, but communicate, send a message, say, "Hi there, sorry we're invisible." Nice to meet you. Let's back up a step. We've already tiptoed through the idea that mirror matter could form atoms, that those atoms could build molecules, that those molecules might self-organize into cells, organisms, ecosystems, biology, evolution. And if evolution plays its patient hand, then intelligence becomes plausible too. That's where the dream begins to shimmer. Mirror civilizations. Imagine them now, evolving on a mirror Earth or across mirror galaxies. They develop tools. They study physics. They slowly become aware of an odd gravitational pull, things they can't see, can't touch, but that tug at their telescopes and satellites, and maybe they start asking the same questions we do. Because here's the curious thing, if mirror life is intelligent, it might be searching for us too. That's not a stretch. We've launched radio signals into space. We've pointed telescopes at exoplanets, looking for biosignatures. We're actively trying to make contact with anyone who might be out there. Why wouldn't they? But here's the twist. We're both using the wrong tools, because their particles don't interact with ours. Their light doesn't reach us. Their signals vanish in the static, not because they're weak, but because they're incompatible. It's like trying to hear violin music through a microwave. So if communication is to happen, it has to break the rules, or at least find a loophole. That's where things get fun. One possible loophole? Kinetic mixing again. That subtle bridge we keep mentioning where mirror photons and regular photons might share a sliver of interaction. If that tiny thread can be pulled, it opens a channel, a whisper tunnel. Some physicists have suggested that, under very specific conditions, mirror particles could emit visible energy through mixing. Weak interactions, fleeting flashes. If a mirror civilization had figured out how to control these interactions, how to build devices that purposefully bridge the gap, they might send signals using hybrid particles, light we didn't expect, signals buried in noise, a flash that appears in the data, unclaimed by any known source, and disappears before you can look again. Here's a lovely little fringe idea. Some anomalous signals picked up by radio telescopes, stray pulses, fast radio bursts, unexplained X-ray blips, have been jokingly attributed to aliens. But what if one wasn't a joke? What if one of those flashes was the equivalent of a knock from a mirror hand? Historians still argue whether the push to search for mirror communication stems from genuine theoretical grounds or just human stubbornness. The refusal to accept that we might be unreachable. But the models are there. The math permits it. The universe hasn't said no. So how might such a message be sent? Well, it wouldn't be binary code through standard radio waves. Instead, a mirror transmitter might modulate mirror photons just enough to produce leakage into our sector. You wouldn't see a beam. You wouldn't hear a ping. You'd see something you couldn't explain. A particle event that seems to come from nowhere. A fluctuation in a magnetic field that violates local symmetry. In other words, a hello you'd never recognize. And if we wanted to talk back, we'd need technology that doesn't exist yet. Devices that generate controlled mirror interactions. Instruments that make particles oscillate between sectors, not randomly, but on cue, a kind of Morse code tapped out in neutron flips or photon leaks. You might be wondering, why hasn't anyone done that? And the answer is frustratingly simple. We don't know how. Not yet. But we're getting closer. Experiments are already probing neutron mirror-neutron transitions. Some labs are scanning the heavens for unexplained photon mixing signals. The groundwork is being laid. The whisper tunnel is being traced, line by theoretical line. And here's a more poetic idea, one that will keep your thoughts warm as you drift. What if consciousness itself is the bridge? Yes, we're wandering into soft speculation. But some fringe physicists, especially those drawn to quantum consciousness theories, have wondered aloud whether minds, not machines, are the medium that some aspect of awareness operates at a quantum level sensitive to mirror leakage. That intuition, déjà vu, dreams, might be the mind brushing against another sector. It's not mainstream science, not by a long shot. But neither is mirror matter, really. And if a mirror civilization exists, and if it has minds, thoughts, dreams, it might be reaching in its own strange ways. You imagine now a mirror researcher sitting in a lab, watching a neutron vanish from a trap they note it, then another. A pattern begins to emerge, too deliberate, too rhythmic. It looks intentional. A message from the other side. You smile, imagining their excitement, and then maybe their confusion, because the sender, that's you, doesn't even know you're tapping on the wall, and maybe, somewhere in our universe, we're doing the same thing, staring at an anomaly, a flicker, a pulse, not understanding, not replying. Yet, quirky fact of the night. In 2004, a theory proposed that mirror matter might account for some of the stranger UFO reports, not by breaking the laws of physics, but by bending the interaction rules just enough mirror vehicles flitting between sectors, leaving gravitational ripples and brief photon signatures. Not aliens from far away, but neighbours from a universe half a particle away. We don't know. We can't know. Not yet. But the question remains, could mirror life talk to us? Maybe not with language, maybe not with signals, but perhaps someday with a particle, a flicker, a shared experiment, a moment where both worlds tug the same string at the same time and pause. Because even in the quiet, even in the dark, we're still trying, and maybe, just maybe, they are too. You're not just floating through thoughts anymore. You're slipping backward now, deep into time, past the spiral galaxies and the dust-swept star nurseries, back before the first planets formed, before the first atoms cooled, before the universe had even learned how to shine. You're headed to the beginning, to the Big Bang's double splash. It's a strange image, isn't it? You've always pictured the birth of the universe as a singular moment, a flashpoint, an explosion, a burst of light and heat and expansion. But what if there were two flashes? Two births? One for the world you know, and one for the one just behind the glass. Tonight you're stepping into cosmology's weird twin nursery, and it's more crowded than you might think. Let's start with the standard Big Bang picture. 13.8 billion years ago, the universe expanded from a singular hot, dense point. Everything, space, time, matter, energy, erupted from this point in a fraction of a second. As it cooled, particles formed. Quarks became protons and neutrons. Electrons found homes in hydrogen atoms. Light finally broke free. All of it happened once, we think. One explosion, one universe, one arrow of time. But now let's tweak that picture. Because if mirror matter exists, and if it truly mirrors all the fundamental structures of our own universe, then it's hard to imagine it popping into existence after the Big Bang, no. The symmetry suggests something stronger. That mirror matter emerged with us. That it was always part of the initial conditions. Like a double splash in a pond, two waves, one visible, one invisible, spreading outward from the same impact. Some cosmological models take this idea very seriously. In these scenarios, the universe began with two sectors. The ordinary one you live in, and a mirror one. Both were seeded with energy. Both inflated, both cooled. They expanded together, separated only by the type of interactions their particles could perform. And here's the interesting part. They didn't evolve exactly the same. Because even in symmetry, tiny differences can grow. Maybe the mirror sector had a slightly different temperature, or a different rate of expansion. Maybe matter and antimatter annihilated a little unevenly in the mirror world, giving it more or less mass than ours. Those early choices, those random little quantum coin flips, would determine everything. How stars formed, how galaxies grew, how quiet or chaotic the mirror sector would become. Historians still debate whether the idea of a twin Big Bang emerged from direct mirror matter theories, or from earlier dual-universe cosmologies that were simply folded into the mirror framework. Either way, the idea has elegance. The math works. It's one of those theories that makes your brain purr, even if your eyes glaze over from the equations. But wait, it gets weirder. Because there's another version of this story. One where the mirror universe didn't just form alongside ours, but backwards. This is the time reversal hypothesis. In some speculative models, the mirror universe is a time-reflected version of ours. In other words, what we experience as moving forward in time They experience as moving in the opposite direction, two arrows of time diverging from the same point, like fireworks blooming in mirrored trajectories. In this framework, the Big Bang wasn't just the origin of space, it was the symmetry point, a kind of cosmic Janus, with two universes expanding in opposite temporal directions. To us, the mirror universe would seem like it's running backward. To them, we're the rewind. Of course, this is hard to test, really hard. Time is slippery, and we can't exactly see across the divide. But it's one of those ideas that wraps around your mind like a Mobius strip. You imagine a mirror civilization watching their stars form, their galaxies expand, their matter cool, while from our perspective they're heading toward the Big Bang as we race away from it. And in the middle, that bright, incomprehensible point where everything begins, and ends, and begins again. You rest in that thought for a while, the symmetry of it all pressing gently on your chest. Maybe the Big Bang wasn't a bang at all. Maybe it was a boundary A handshake, a collision where two worlds bounced off each other and unfolded in mirrored spirals. And if that's true, then the early universe might be full of evidence, echoes, tiny asymmetries in the cosmic microwave background, unexplained fluctuations, patterns we can't make sense of, but which might make perfect sense in a mirrored context. Here's your quirky fact of the night. Some researchers have proposed that unexplained anomalies in the early universe, like the so-called cold spot in the cosmic microwave background, might be artifacts of interactions with a mirror sector, not full-on collisions but gravitational coupling in those first moments of expansion, a slight drag, a shared ripple, and that leads to a provocative idea. What if the mirror universe left scars on ours? Not visible ones, not wounds, but gravitational imprints, structural fingerprints, regions of space that evolve just a little differently because of interactions with the twin that pass silently alongside them, just long enough to leave a mark. You imagine that now, galaxies that formed faster in certain places, stars that burned hotter or lived longer, not because of randomness, but because the mirror universe tugged them ever so slightly before drifting out of range. And maybe we've already seen those differences, maybe we've already mapped them, maybe we just don't recognize them for what they are. Yet. You settle deeper into your blanket now, drifting alongside that twin expansion. Two universes side by side, one made of light, one made of shadow, both born from the same instant, both filling their own skies with stars, and between them, a boundary you can't cross, a silence you can't break, but the symmetry remains, even here, even now, even as the night gets darker and the universe grows ever wider. You're awake, but only barely, curled up beneath layers of thought, drifting through the strange space between dream logic and cosmic logic. And now something tumbles into your imagination with the weight of both terror and curiosity. What if a mirror meteor slammed into Earth? No, not a Hollywood fireball, not a glowing streak across the sky. Because remember, mirror matter doesn't burn in our atmosphere. It doesn't interact with light. It wouldn't spark, it wouldn't roar, it wouldn't glow. It would fall, perfectly silent, perfectly invisible. And yet, it could be disastrous. Tonight, you're in for a very weird ride. A theoretical crash course in what might happen if a chunk of mirror matter, say, a mirror asteroid the size of a car or a city block or a mountain, suddenly barreled toward Earth. To begin, let's break down what makes ordinary meteors so dramatic. When a rock from space enters Earth's atmosphere, it compresses the air in front of it. That air heats up, glows, and creates the bright streak we call a shooting star. If it's big enough, the rock survives the descent and slams into the ground, releasing energy from impact and kinetic shock. But a mirror meteor, it doesn't interact with air, not electromagnetically anyway, so as it plunges into the atmosphere there's no friction, no heat, no light. It would pass through clouds like they weren't even there. In fact, you wouldn't know it was coming until it arrived. Now imagine a city, midday, sunny, a normal Tuesday. And then, without warning, the ground shudders, buildings rattle, somewhere underground, deep beneath the crust, something slams into solid rock. But there's no crater, no fire, just a blast wave. Seismic, sudden, unexplained. That's the Tunguska event all over again. In 1908, something exploded above the Siberian forest with the force of a 10 to 15 megaton bomb, flattening over 2,000 square kilometers of trees. Yet no crater was found. No meteoritic debris. Nothing. One theory, you guessed it, a mirror meteor. If a piece of mirror matter entered our atmosphere and retained enough kinetic energy to penetrate the crust, it could have deposited that energy below ground, heating rock and air and generating a pressure wave powerful enough to blast outward, like an underground bomb with no fuse, and that's just the mild version. Let's say the mirror meteor is bigger, 1 kilometer wide, that's extinction event scale. Still no glowing fireball, but as it hits, its gravity alone would pull on nearby matter. Mirror matter still bends space-time, remember? It has mass. So as it plunges toward the surface, it might cause strange, localized tides in solid ground. A warping, a flex. Then it impacts, directly into the mantle. The surrounding rock, unable to compress or heat the mirror mass, just gives way, and now you've got a chunk of ghost matter burrowing into Earth, carving out a path of gravitational chaos as it descends. If it's dense enough, it might even settle near the core. And here's where the long-term consequences get truly strange. Because that chunk doesn't just vanish. It stays, it has mass, it pulls. Maybe it interacts minimally with normal matter, enough to cool nearby rock. Drawing heat away, geologists might detect unexpected cold spots. Maybe it subtly alters the motion of molten iron. Maybe, just maybe, it disrupts Earth's magnetic field over decades or centuries. Historians still debate whether the mirror impact theory was born purely from attempts to explain Tunguska, or whether it emerged independently from cosmological speculation. Either way, it's one of those ideas that sounds like science fiction, until you realise the math doesn't object. Now here's a quirk for you. In 2002, physicist Robert Foote, yes, real name, real person, proposed that mirror matter meteors might explain not only Tunguska, but also other odd seismic events, ones with no seismic source, no plate movement, no nuclear detonation, just sudden underground jolts. You'll find papers about this in the niche corners of astrophysics journals. The footnotes get weird. But let's take it further. What if we found one? Not by sight, of course, but by mass. Imagine a region of Earth where gravity is slightly stronger than expected. Instruments pick it up. Satellites confirm it. But there's nothing there. No mountain, no dense mineral deposit. Just a patch of forest or ocean that seems to weigh more than it should. That might be a buried mirror object. Or imagine this. During a mining operation, you dig deep and suddenly find equipment behaving strangely. Metal cools inexplicably. Electronics glitch. There's no radiation, no known cause. You detect a cold, dense region. But it can't be isolated, can't be touched, can't be seen. The crew leaves. The hole fills with water, years pass, and the story becomes folklore. The invisible mountain, they call it. Weirder still, what if a mirror object didn't stop in Earth? What if it passed straight through, exiting on the other side? It might slow down, settle in the centre, or it might drift out the other side with minimal energy loss. Imagine tracking gravitational anomalies and finding them moving through Earth like a ghost train on a buried rail. The good news? Mirror matter impacts wouldn't cause the same firestorm and shockwaves as regular asteroid strikes. The bad news? They'd be unpredictable, undetectable, and completely unpreventable. You roll a little in bed, imagining a mirror boulder the size of a stadium silently drifting toward Earth, unseen by telescopes, uncaring about atmosphere, waiting to dive straight into the mantle like a ghostly torpedo. And yet, we don't live in fear of these things. Not because we're brave, but because we don't see them. Out of sight, out of mind, literally. Still. We might be watching effects, seismic events, magnetic drift, gravitational anomalies. We might already have the evidence, we just haven't looked at it through the right lens. Or mirror. You settle deeper now, letting the tension fall away. After all, if one were going to hit, it probably would have done so already. Probably. You're nearly weightless now, drifting between thoughts, slowly turning in the low gravity of curiosity. Around you, the dark is quiet, but it hums, not with sound, not with voices, but with possibilities layered one atop the other like soft dust. And now you face a question as strange as it is personal. What would it feel like to touch a mirror object? Not see it, not theorize about it, but physically come into contact with something made of mirror matter. What happens if you hold it in your hand, if you press it to your cheek, if it's dropped on your toe? Let's play this out. You're in a lab, or maybe your backyard when you come across it. A mirror object. You don't see it, because mirror matter doesn't interact with visible light. You don't smell it. You don't hear it. It has no temperature you can measure. It's like a hole in the air, but then something catches your attention. A distortion in gravity. A pull on the spring of a nearby scale. A small object, maybe the size of a coin, sitting on a surface and weighing more than it should. You place your hand above the spot. Do you feel anything? Maybe a faint coldness. Some theories suggest that mirror matter, if it interacts weakly with normal matter, might absorb heat. It wouldn't feel hot or cool like metal. It would feel empty, like heat draining away without friction. You lower your hand gently, and then something odd happens. It passes straight through. No resistance, no sensation, no texture, like trying to grab air that forgot how to exist. Because remember, all the forces that make objects feel solid, electromagnetism primarily, aren't shared between regular and mirror matter. There's no charge repulsion, no atomic bounce. Mirror atoms don't recognize your atoms as solid at all. They just glide through like you're not there. Imagine that, holding your hand in place, seeing nothing and feeling nothing. And yet, the scale beneath you shows weight. A small dent in a pillow, a leaf shifting in the windless air. It's real, but untouchable. Now picture trying to pick it up. You scoop your hand under where the object should be. You close your fingers. There's nothing inside, but the object doesn't move. It remains on the table, because despite being invisible and intangible, it's still affected by gravity. You can't grip it, but you can move it, with tools, not traditional ones. A metal spoon would fail, but imagine this. A trap built from gravitational gradients, a hollow sphere with controlled magnetic fields to influence tiny mixing interactions, an electromagnetic cradle that nudges mirror matter ever so slightly. With the right tech, you could manipulate it. Not handle it directly, but shift it, like levitating a soap bubble in a sound wave. And if you could trap it, study it, well, the science gets exciting and a little bit absurd. Some researchers have proposed that mirror matter embedded inside ordinary materials might cause subtle distortions. Glass that refracts light slightly wrong, crystals that bend oddly under pressure, composite materials with unexplained thermal loss. If mirror matter mingled even faintly, it might show up in the real world as anomalies, things you'd ignore until you couldn't. But what if, hypothetically, you could touch it? What if, under the right conditions, a mirror object brushed your skin with a small interaction coefficient? Here's where it gets surreal. Some theories suggest a momentary cooling effect. Mirror matter might steal your body heat, not by conduction, but by neutralizing the energy at the boundary, a chill with no airflow, a shiver with no breeze. Your body doesn't scream in pain, it doesn't even flinch, it just adjusts, like touching shadow, and that's just for stable matter. What about more complex structures? Imagine a mirror feather, a mirror ball, a mirror gear, spinning in a mirror machine. Entire tools that work on their side of the universe, completely unusable here, but functional there. What would those feel like? You'd never know, unless you could bridge the gap. That's where oscillation comes in again. The idea that under certain quantum conditions, particles can switch identities. A neutron here becomes a mirror neutron there. A portal not of doors, but of behavior. Imagine building a chamber where a small object could oscillate back and forth, flickering between sectors. You wouldn't see the transition, but you might feel something. A ripple in the field, a vibration in the force, a moment where the air feels dense, like walking through a humid room with no moisture. Some call it a quantum flip zone, a hypothetical space where interaction is enhanced. There's no proof this exists. But if it did, you might be able to touch a mirror object, not by force, but by entanglement, a dance of particles, momentarily synchronized. Still, even in your most optimistic dreams, it wouldn't be satisfying. There'd be no friction, no texture, no weight in your palm. Touching mirror matter would be like reaching into a reflection. It's there, but it's not here. And yet, the consequences are very real. You've got an invisible object exerting weight, cooling its surroundings, ignoring your atoms, and it's just sitting there, minding its business. Could you build with it? Could you use it? There's a fringe idea, of course there is, that advanced civilizations could use mirror matter as structural ghost tech, to store mass in places that don't take up space in our world, You could, in theory, hide mass, or energy, or even entire machines, all within your own living room completely unseen. A mirror vault, a mirror engine, a mirror city, just offset from your own, touching nothing but shaping everything. And here's a tiny historical tidbit. In the 1980s, some engineers speculated that mirror matter, if it existed and could be anchored, might make for ideal space shielding. Since it interacts only gravitationally, it wouldn't block solar radiation, but it could deflect physical impacts ever so slightly. A force field made of mass, not magnets. So, could you wear it? Could you sit on it? Could you build a chair from mirror wood? Not likely, unless your body also had mirror components, or unless you somehow hybridized your atoms. Sci-fi, yes, but we're already most of the way down that rabbit hole. Instead, the best way to feel mirror matter is to measure it. Track the dent it leaves in a gravitational field. Watch the way it warps time, ever so slightly. Observe the heat it drains. The world is full of things we can't touch. Black holes, neutrinos, dark energy. Mirror matter joins that list not as an idea, but as a presence. A shadow with weight. A ghost that trips scales. You reach out again in your mind and there it is. Still there, still silent, still untouchable. And yet, somehow, impossibly, very real. You've reached the quietest corner now, the softest edge of thought, where even speculation slows down and starts to breathe deeper. You've passed the stars, the science, the strange suggestions, and now you lie in the dark with one final whispering possibility curling its fingers around your sleep-heavy brain. What if the universe has a twin soul, not just a duplicate, not just a cosmic clone built from mirror particles, but a true partner, a matched half, a hidden balance, folded alongside us not just in mass and energy, but in meaning? Yes, we're slipping into metaphor tonight, but the thing about physics is that the closer you get to the edge, the more it starts to sound like poetry anyway. From the very beginning, mirror matter was about restoring symmetry, balancing what felt broken, making the universe whole again by giving it a reflection that plays by all the same rules, just in reverse. It's beautiful, really. Because what mirror matter asks us to consider, beneath all the math, all the field equations, all the gravitational nudges, is that our universe might not be alone, that it was never alone. That right here, not across space, but across interaction, there's a second version of everything, of every atom, every wave, every possibility, including perhaps every you. You roll gently, letting the idea stretch itself out beside you, a twin soul to the cosmos, another Earth, silent and unseen, twinned with ours across a dimensionless veil, another galaxy, another sky, a mirror moon pulling on mirror tides, mirror forests breathing mirror carbon dioxide, mirror hands reaching for tools built from unseen elements, mirror thoughts, forming mirror questions, lying on mirror pillows beneath mirror stars. They don't see us, we don't see them, but we share gravity, we share motion, we share beginnings. And just maybe, we share a purpose, though we'll never speak it. Because here's the thing about mirror matter. It's a reminder that the universe may not be built for visibility. It may not care about what can be photographed or named. It may care only about balance. It may be writing stories in two languages at once, one we know and one we'll never translate. But that doesn't mean the other story isn't real. In fact, it might be half the reason anything makes sense at all. You let your mind wander through that twin possibility. Maybe that's why the equations feel incomplete, because they're only telling one side of the story. Maybe that's why symmetry keeps showing up in physics, over and over, no matter how deep we dig. Not because it's convenient, but because it's fundamental. Nature likes balance, it likes mirrors, and maybe, somewhere along the way, we forgot that. There's a quiet tradition in theoretical physics, the idea that if something is mathematically beautiful, it's probably true. Not always, but often enough to take seriously in mirror matter. It fits that mold. It's not just a fix for dark matter. It's not just a playful extension. It's necessary if you want to make the universe fair again. Historians still debate whether mirror matter is physics or metaphysics, whether it belongs in the laboratory or in the realm of high-concept dreams. But either way, it invites us to look at our world differently, not as isolated but as half of something larger. Quirky tidbit of the night. Some philosophers of science have proposed that if mirror life ever discovered our existence, they'd call us the dark matter, the mystery, the missing mass. Maybe their astronomers are staring at gravitational lensing data, wondering what invisible civilization is tugging on their stars. Maybe they write scripts like this one. Maybe one of them is lying in bed right now, wondering if there's more, wondering if there's a second universe layered beside theirs. A twin soul, just like you are. You breathe slowly now, letting the weight of the cosmos settle on your chest. Not heavy, just constant. Like a mirror pressing gently against your back, reminding you that you're not the only version of yourself that might be dreaming. And in that stillness, you let go of the need to know. You don't need proof. Not here, not tonight. It's enough to wonder, to suspect, to imagine the universe not as a lonely firework, but as a pair of candles, lit in the same moment, burning in silent symmetry across the veil. One light for the visible, one for the unseen, balanced forever.